back, and I'm really, looking forward to discussions with you today. And I'm also, really honored to be able to, contribute to this amazing facility. Well, as you know, last year we celebrated 30 years of user operation. And this year we will be celebrating 5 years of EBS operation. Very nice events. Maybe so, I will have mainly two parts in my presentation. First one will be, some statistics and news from the ESRF. And the second part will be a little bit more about, our strategy for the future. And of course, we share the presentation with Rema and Michael, who will give you more, insight into, all the project science and so on. So some statistics. So first of all, proposals. So for the proposals we received in September, we almost established a record, which is, very good because, previous one was, just before the EBS where people were trying to secure beam time, but also when we did not have, as many hubs and bags that we have now. So it's probably a true record. And also it was the first time we were using the first module of the new user portal. And you will tell us, but apparently it went quite smoothly. And I would like to thank again the user office and all the teams in IT for this achievement. Almost 10,000 user visits last year. So again, something which is really, really nice. And you can see here on the slides, I will try to use a mouse because I guess it's better for people being online. More than 1/3 of the experiments being carried out remotely, and a little bit less than 10% in hybrid mode, which is, I think, something which is really nice to have. To allow, some people to be here while the others contribute from their lab. Publications, maybe I can go to the next slide. Number of publications is now increasing with, what I would call EBS publications, and of course with the publications from the previous source going down. More than 40,000 publications since 1994. And because you have just, got the last edition of the highlights, I think something like 2,000 of them being featured in the highlights. And also, with a large number of publications published in journals with impact factor higher than 7. And I will not, talk too much about science. This will be Rema and Michael, but I can't resist saying a few words about the 2024 Nobel Prize in Chemistry with, two of the people being awarded this Nobel Prize, David Baker and John Jumper, having co-published with, the ESRF in the, and of course with AlphaFold, where, the ESRF was either used to confirm, predictions from AlphaFold, or, being used also to complement AlphaFold predictions for, some more difficult structures. And also not forgetting that AlphaFold would not have been possible without, training with the protein data bank, to which we are the first contributor by far in Europe, only second to the APS in the US. So that's again something which is an achievement, I think, of the facility. Machine, So unfortunately, I mean, beam time statistics in 2024 were in fact quite good, close to 98% availability, but not as good as we used to be in the past for, I mean, different reasons, but in particular, aging of some components, in particular in the injector. I mean, the issues have been identified and we have solutions, and I will come back to this in a few minutes. But we also established end of last year a new record in, I mean, number of hours or days without a single failure, close to 23 days. And I think we were also very close to even a more impressive record this year. Unfortunately, we had, I mean, a beam loss last week that ruined that, but sure, we will establish new records soon. And in any case, the machine is quite efficient and reliable this year. Maybe also I would like to say that, I mean, with the now having replaced all kickers and kickers chamber, we are now again to reach 90 milliamps in 16 bunch mode, which was, I mean, the target and is now possible again. Now, I mean, so this was for the news, and you will have a little bit more statistics on publications and science in the directors of research talk. But I would like to, I mean, share with you some ideas regarding the strategy and the vision for the future of the ESRF. And I mean, we believe that, I mean, the success of the facility relies on those different elements, which are really, I mean, the pillars of the strategy. First of all, obviously, I mean, beamline and accelerator upgrades. We now have the EBS, which is fantastic. But as I just told you, I mean, all accelerator components have been upgraded, and we are facing some issues and working on them. And also, I mean, regarding beamlines, some of them are, I mean, still in the state as they were something like maybe 20 years ago for some of them, and need to be upgraded, and we have a plan for that. I mean, of course, I mean, for that, we need, I mean, all the enabling technologies with, in particular, I mean, very strong effort on detectors, but also optics, mechatronics, robotics. I will also come back to this. What is fantastic with the EBS is that, in particular, also with the high throughput, it allows, I mean, new ways to work together with you, possibly in a more collaborative way, which is what we are doing with the new bags, you know, beyond, I mean, structural biology, and also with the EBS. And this is, we think, quite important, and that, I mean, working more closely together, we can have higher impact. Data are obviously, I mean, the main element in the strategy for the coming years. With the EBS, we are, I mean, producing an enormous volume of data, which is really an opportunity to advance knowledge beyond what has been done in the past, if we are able to, I mean, fully exploit them. And I will show you a little bit what we are doing in there. Of course, all that would be useless if we were not able to operate the facility in a sustainable way, and also if we were not able to, I mean, train the next generations to make the best use of it. Again, Rema and Michael will tell you about this. So now, going quickly through all those areas, starting with, beamlines. So you might know or remember that in 2024, we have put in user operation 2 new beamlines, ID03 for, hard X-ray microscope and ID14 nuclear scattering. There was, a very nice tutorial yesterday on the capabilities, new capabilities brought by the new ID14. The ID21 nanoscope has been open to user. A second cryo-electron microscope has also been put online. This is a French CERG, and you see, the photo here of the inauguration. The new large sample stage for BM18, just to tell you, it will be capable of holding samples of 300 kilos and 2 meters high, is now under commissioning, and the civil work for the future ID18 beamline has also started, and we already have a very high quality slab for that beamline, which will be critical for its success. Accelerators. So as I was telling you, a number of refurbishments are planned. In particular, LINAC, we have some issues with LINAC, will be refurbished. We will also have, a light upgrade of the booster ring, where we also need more spares, and all this to, safeguard the operation of the entire facility. We have just, and this is a project which has not been made, we have not made a lot of noise about it, but which I think is really nice, is this hot swap system for power supplies, which really allows to swap in real time when needed. So this will obviously improve reliability, availability, sustainability. We have this now eco mode, which is always used and allows again to save some energy. Brightness and coherence. We have new prototypes of undulators, for example, with vertical polarization. We have the undulator monochromator synchronization project, which is critical for many beamlines, in particular for absorption spectroscopy. And we are also starting to explore the high temperature superconducting technology for insertion devices. And last but not least, we will also be able now to start the fourth harmonic cavity project, which will improve in particular lifetime with all the benefits which will go with this. Enabling technology. So I can't discuss everything. So I just decided to highlight 2 types of projects. Our new double crystal monochromator, which is really fantastic in terms of accuracy, stability. We have 3 operational, 2 under construction, and this is really bringing a higher level of performance. And detectors. So detectors are of course absolutely essential to make the best of the new ring. So we deploy commercial detectors, and in particular new types of detectors like this Citius, which is a collaboration between Springate and Sony, which we have also tested here and will bring again more. SmartPix, which is our in-house developed hybrid pixel detector using, the Medipix 3 CERN chip, which will be deployed at 6 new beam lines in 24 and 25, and some projects. One, which is a LEAPS Enough project, is a new, germanium detector for spectroscopy. And we also have, a collaboration with Daillant, XFEL, and other partners for a new generation of detectors for high energy diffraction, using CDZNT sensors. New access modes, I will not, talk too much about it, but you know that we now have, extended the bags to more areas. And a very nice one, which has been launched in 24, is the Chronos bag. You will have, a presentation this morning, so I will not say more, except maybe that the bag coordinator is the awardee of last year, young researcher, and I'm very happy with that. Not because I was chairing the committee, but because, she's now, taking over and taking full responsibility for the bag. Hubs, we have started the, second phase of the battery hub also in 2024. And we really believe in those new access modes. And Rema and Michael will repeat that, but we, strongly encourage you, to talk to, beamline managers, group leaders, and also, among you, to launch new hubs and bags. We are really open to it, and we think we can really make an impact with them. Data strategy. So that's really, I think, the heart of the strategy for the coming years. And we, so you have some figures on the left. Huh? So we have now, I think, more than 23 petabytes stored. Maybe, something I would like to emphasize here is that, we try, to have data which are as fair and open as possible. And I think a real success is that, if we look at the paleontology portal, I think we have, a little bit less than 400 publications there. And I think now almost 60 have been written by people and published by people who have been using ESRF data, but never participated in any experiment. So really, using open data for their publications, which I think is also a trend that, we need to follow, but this is very encouraging and, supporting, our strategy. Now, what we have in place now is, I think, a full ecosystem of software to help you in your data collection, analysis, publication, and so on. So starting with Bliss for, beamline control, and now, almost all our beamlines are using Bliss, if not all of them. Lima 2, which is, the new, detector software. Again, yesterday I was attending the XPCS tutorial, and I learned that, with an experiment finishing this morning, they had a data set which volume could be reduced from 360 terabytes to only 10, just using Lima 2 and its advanced features. So again, an amazing development. We have the e-logbook, which allows you to integrate, your data there and also in data catalog. We have eWalks, which is the workflow system, which allows, real-time analysis, even, in feedback loops. And this has been done last year. we have Visa for data analysis, and we have, the data catalog. So, we, of course, need to further develop all those tools, but, the effort, is there really, extremely significant. And again, all the teams involved should be congratulated for that. Of course, I can't speak about data without, also mentioning cybersecurity, which is very important to, secure the operation of the facility. So we have a number of, sub-projects there. I will not go into the details, but be sure that this is a high priority here at the ESRF, and that, we are doing everything possible to make, a safe operation regarding cyber threats. A few words about, sustainable development. So you know that, with the EBS and use of permanent magnets, it was possible to reduce the electric consumption by something like 25%. But this is not, the end of the story. So last year we have, completed the thermal insulation of the guest house, which, those of you who are staying there have probably noticed. We have also installed, a heat pump to, reuse the waste heat for the accelerator to heat the experimental hall, also resulting in something like saving almost 5 gigawatt hours per year. We are working now on on-site solar panels, and we are also, completing a new, greenhouse gas emission survey, which will allow us to see exactly where we can make further progress. So this is almost the end of my talk. I have only one slide left, and I have to, share with you some quite important information regarding, funding and funding strategy. So, as you, can imagine, like, all of the facilities in Europe, we have experienced a loss in purchasing power due to the, inflation following COVID-19 pandemic and international crisis. And this resulting in something like a misalignment of about 5 million euros between expenditure and funding. And as you can also imagine, most of our, or many of our partner countries are also facing, serious economic and financial difficulties. And so the problem can't be solved only by increasing the budget. And so the, Council has worked a lot on this, establishing a working group to find solution. Also, together with SAC and MAC, and came to a resolution at the last meeting in November, which consists mainly on 2 parts. One is to, reduce the user mode by 7 consecutive days and putting 2 beam lines on hold, just to make, operation sustainable. But at the same time, the Council also, recognized a strong need to reinstate some critical investment, which is absolutely critical for, the success of the facility. And there we have, 3 main elements. One is, this injector refurbishment I already mentioned, and the 4th harmonic cavity, which will, ensure, smooth operation of the facility. Second is, construction of a life science nanoimaging beamline, which has been ranked extremely high by the SAC, and you will have all the details in Rema's and in Michael's presentation. And the last one is, of course, the required hardware and infrastructure for the efficient exploitation of the data. I would like to thank again Francesco, who was extremely instrumental in all the discussions there. And so thank you again, Francesco, for that. So obviously, you see that we are facing difficult times, in particular for, the staff of the beamlines, which will have to be put on hold, and their users. So this is not right for now. Full effort should be in place in 27, and more or less half of it in 26. So we have time to adjust. There is a SAC working group which has, established to identify the least hurting solutions, and they have started to work. But we can also count on, I think, the strong support of, all members and associates and partners. As an example, this exceptional contribution has been voted unanimously by the Council, which really shows in the difficult times for economy in Europe at this time, a very strong support. And the ESRF has faced similar issues in the past, and with the help of all stakeholders, has always managed to, get through and get out, of the crisis stronger. And I'm confident that this is what we will be able to achieve together. And with that, thank you very much for your attention.
Good morning, everyone. Thank you for joining us, and welcome to our user meeting 2025. I want to thank everyone who made the effort to be here with us again. Also the ones that have been in charge of giving the talks for the preparation of this, the presentation and the poster. Then also all our young, scientists that they are so enthusiastic to join this meeting, and the senior ones, because we are very lucky. We have a quite important battery of, many people that actually contribute to be here today. And I would say for the young scientists, it could be great if they can get their, insights for the future. So use this period to get the most from the meeting. And just I take the chance, this is not normal, but I do it to thank the organizing committee, the user organization for this excellent meeting, Stephanie and all her team for all the effort behind these 2 dates. It has been a 1-year work. And with that, on behalf of Michael and myself, we are going to share some latest developments from the experiment division. And also, we take the time to celebrate 30 years of science. And in that respect, actually, what I will show is just a collective effort, is the joint and strong collaboration between the staff, but most important, users, who actually there's a kind of closed loop there, feedback all the time given to us. And in that context, let's take a quick look to the key milestone over the last 3 decades. I think that everything is starting by 1988 with the signature of the convention. Then the first user meetings actually in 1989 took place, and since then it's a non-stop journey. The first being in the electron, the first electron being circulating in our storage stream by 1992. Officially, the user service mode started in 1994 with 15 beamlines. And the progress of the developments and also the science coming out was published for the first time in the highlights in 1995, then in the ESRF newsletter in 1996. By then, we already have 10 to the 20 photons, a square millimeter, a square milliradian, 0.1 bandwidth, brilliance, with 200 milliamp, and well, emittance that it was horizontally by 4,000 picometer. And by 1998 already, we got an expansion to 40 beam lines. And there was an important milestone by 2009 when ESRF decided to go for the phase 1 of the upgrade program. And the very same year, actually, we were very proud of our users. 2 users were awarded with the Nobel Prize in Chemistry for their groundbreaking work on ribosome. Later on, in 2012, actually, another Brian Kobilka user got as well the Nobel Prize by the work on G protein coupled receptor. And that year, precisely, the ESRF released the revolutionary design of the hybrid 7-band achromat lattice, which is actually the foundation for many upgrades all over the world. Well, this continues, and in 2015, we had actually the launch of the second phase of the upgrade program with the EBS. And then by 2017, we have already 44 beam lines with the Criado EM. And in 2018, we have the 20-month shutdown for the implementation and commissioning of the new storage ring, the EBS. That actually restarted. Here you have the beam in the storage ring by 2020 with 10 to the 22 photons. It was a record time within budget, quite a little ahead. And this has been the effort of our staff, and it's amazing. Since then, actually, we then faced the COVID lockdown that again challenged our operation for the user experiments. We went through remote access. Well, the last 3 years, it's non-stop in science and the development of new capabilities for these users. In 2024, we celebrate the 30 years anniversary. And again, as was mentioned before by Jean, 2 of ESRF collaborators got the Nobel Prize for their protein design, where ESRF has important contribution. So, and last year, we had before this one, a very successful user meeting. So if we want to talk about science, I think that if we use the covers of our ESRF news, we have a window, to the evolution of the ESRF in terms of technology, in terms of user community, in terms of science, modality, everything. So I will just show everything started actually in the newsletter of ILL, our brother. Then we passed through all the newsletters that showed our, let's say, contribution to diffraction, high pressure, cultural heritage, ondulators development, domain, magnetic domains, SNO, the microtomography by 2002 with cellulose and ID1, for instance. Then we went through more about structural biology, soils. We start working with the industry, which is one important direction. Since then, environmental science, the new upgrade phases, catalysis with becoming, we are closely moving to global challenges with the research, batteries, on life, academic again, and industry. We talked in 2011 already of data challenges. Since then it's a major concern for us. Nanometers, we moved to nanometer scales, to time resolved measurement, to high energies for more operando experiment in situ. So it has been a long journey. I think that we see the transition clearly to more capabilities, to new research fields. And in that context, it's a non-stop. We are always pushing the limits of our instrument, but keeping a high quality, and that's the most important. We need data with very high quality, actinins, superconductivity, brain research. As I say, quality is a must, and this is the EBS. COVID research, COVID, our contribution to COVID through high pressure science. Well, as you know, there's a quite important development all over the years, including today serial crystallography in ID 29, green circular economy, connectomics. So if you follow just the cover, you see the path that we have followed over the years. And this is thanks to the close link among user and the facility. Okay, let's focus on 2024. In 2024, if you just concentrate on the subject that we have been dealing with you, we see that the ESRF has contributed to the climate change, sustainability, carbon capture, sustainable energy, battery research, environmental contamination, in terms of fundamental science, always for, topological quantum materials, also novel biological insights, as we mentioned already, the protein decoding, it was a really big achievement with the contribution of the ESRF science. The health and medicine, we have the Human Organ Atlas, for sure. It's giving us a lot of results, but also across many lines on heart, brains, emerging disease, fertility, and so on. Those are just a snapshot of the results that we have got in the last year. In the same sense, we find it for industry, catalysis, additive manufacturing, advanced materials, and environmental science, pollution, toxicity, food, plants, and, food safety. So let's say the research continues using, the same perspective as before, but this time with more, let's say, impact than before, because we are just focusing in those areas where the ESRF could make a difference. And all right, that was just basically the science done in 2024. If we just look at the statistics, as was mentioned before, in 2024, we have a quite big number of proposals. The difference is, compared before the shutdown, is that today we are running quite a lot of bags and hubs, and if you sum up everything, you can, since they group quite a lot of experiments, you can be sure that the demands from the user are pretty high. And for sure, there is a dynamic, a clear interaction between the proposal submitted and the proposal allocated, the chief delivery. In that sense, I could again call for your attention to use these 3 days to get in touch with the scientists, to explore new avenues for creating bags and hubs or any other kind of LTP or long-term proposal that could facilitate and go faster in science. So we are open to any initiative that can help to get access to the BIM. We recognize the effort done, over the last years with the TID and the user office for the launches of the first module of the portal, which actually optimize the access and make easy user to conduct their experiments. We continue because there's 8 modules and this is only one. What else? In terms of actually in major developments, I want to just highlight the completion of project that has been started actually before I arrived. I mean, ID3, the hard X-ray microscopy, that was before in ID6. The new Daillant for nuclear resonance scattering, open to users since February. The new microscope, ID21, which actually start user experiment this year. The new cryo-EM that will give a talk later by the being responsible. The compact new X-ray emission spectroscopy in spectrometer in ID32, and as was mentioned before, the final test of the large, very challenging equipment, the large sample state for BN18, which is a real technological, let's say, breakthrough, I could say. And with that, Michael, it's your turn.
Need the medal. Again, warm welcome from my side as well, and we are really happy to see you here, the old faces, the new faces, the young faces. And well, there's a lot of things that have been accomplished, and I think we can all be proud of what has been done in the past, but it's not over. We are in a new phase. We're in the phase of the absolute exploitation of this unique source. And for that, already we have in 2024 done some important developments on the source side. We are back for those who use the timing mode, back to nominal current in 16 and 4-bunch mode, thanks to an effort of the Accelerator and Source Division. As Jean mentioned, a record year in 2024 to commit funds for new detectors. In terms of instrumentation, we continue our ambitious enabling technology program to really provide the beamlines with the best performance possible. A lot of efforts around in a sample environment. Spec to Bliss migration has been already mentioned. Specifically, we would like to emphasize Lima 2 as well as EVOX, that are really tools that have been developed in-house that really are aiming uniquely to make the user experience even better, and a couple of spectrometers and end stations that we currently have successfully implemented. But it's not over. Again, we come into a cycle where the emphasis is on the scientific exploitation, but keeping in mind the part of ESRF's success over the last 30 years of user operation was a regular and continuous upgrade of the beamline portfolio. So we have finished almost the refurbishment of the ID26 optics. We started an ambitious refurbishment of the coherent part of ID10 and strengthened links to the coherent program on ID2, the small angle scattering beamline. We have kicked off the technical design report for a refurbished ID11, and ID12, ID13 will start very soon work on a refurbishment that starts with a conceptual design report. And as Jean was mentioned, one of the top priorities is the conclusion of the conceptual design report for our new nano-imaging beamline on port ID18 that has top priority and can be seen as the first post-EBS upgrade beamline. And just to recall, it's really one of our strategic goals to get this new nano-imaging beamline for life sciences already up and operating, bridging from cell biology to connectomics, really a field of integrative biology from the molecular level almost up to the whole human body, exploiting, of course, not only ID18, but of course the other beamlines that contribute to that. As a recall and credit goes to the two consortia that came out, as Jean mentioned, top ranked and followed by a strong recommendation by the Scientific Advisory Committee, by two consortia led by the EMBL and the Krisch Institute respectively, really bringing and bridging communities, and that is reflected as well to the micro symposium that will be held tomorrow on that topic. There's a lot of challenges related to that beamline, but it's not only related to that beamline. It's actually related to all our beamlines that comes with a price we pay with ESRF-EBS in terms of sample damage, heat management, data overload, detectors, and high precision and alignment. But we are ready to address these challenges. We have these wonderful technical and engineering divisions that support the experiments division with their capacity and their expertise, and being able to provide the technologies of today and of the future. So big thanks at that point as well to all the colleagues from these divisions. Looking further ahead, and as Jean introduced, the success of the ESRF on the 5 to 10 years horizon is clearly hinged and rooted in the promotion of scientific excellence through the optimum exploitation of ESRF-EBS. That goes hand in hand with beamline upgrades, the enabling technologies that are driven by the scientific needs. Data will be a key element and will make a difference where we stand with the data analysis tools that provide meaningful data to be analyzed and brought and matured into publications with impact to the user community, to the scientific community, and to society at large. We believe that specifically ESRF-EBS, the completely new windows for new service for industrial clients that are not yet fully untapped. And we will focus on this in the few years to come, including support to other facilities that are closed down. We're currently supporting commercial clients from PSI, and that's a model that we would like to offer to the other facilities that go through an upgrade in the future. Key as well is to have the brightest minds coming to ESRF as users, but as well having the brightest minds working at the ESRF and use the ERS as a key element in the scientific career. So user outreach and training the next generation is very, very, very close to our heart, and we put emphasis with Gemma and I on this specific aspect and the links to training and education. And we've used this opportunity to point that we have a long-standing joint effort to train undergraduate students through a summer school. I think we are running into the 11th edition of it this year. We have Hercules European School training young scientists in the use of neutrons and X-rays, both from free electron lasers and from synchron-based sources, running since 1922. But on a regular basis as well, we offer student summer jobs, get a first immersion into the scientific life of a facility for a duration of about a month. We would like to advocate even more our traineeships that are open to master students in all our partner countries. We really is a unique opportunity, a decisive step and decisive decision to be taken for your scientific future. And of course, our PhD program that has several elements, including internal calls for projects, but as well programs that are supported and co-financed by the European Commission. So please use these days at the ESRF here to talk to our scientists, talk to people that are students, and really build up a program with them that would then be offering a traineeship jointly with you at the ESRF for a PhD. Then come to the conclusion. It's a special year again. It's 130 years since X-rays have been discovered, almost 80 years that synchrotron X-rays have been observed for the first time. We look back to exactly 50 years when the idea of a European third generation synchrotron source came up. We look back to 30 years of user operation, a fantastic light source, and a bright future, I think, ahead of us. And congratulations by Gemma and I to the ESRF user community and the ESRF staff for 30 years of excellent science. Thank you very much. Well done. And with that, we thank you for your attention.
So yeah, we can shift to questions if you have questions in the audience for directors. No questions? Everything was clear. And again, I will start. I will go keep this one. Yeah. Yeah.
I saw that there are 3 beamlines on hold. Which is the time scale? Well, there were 3 red on your things, but anyway. Okay, sorry. Okay, perfect. So my question was on the time scale of resuming back and put them back into.
Good question. I think for ID 18, as I mean, Michel and Gemma mentioned, this is quite a complex project. So it will take at least a few years to, I mean, bear it. Let's say, hopefully, well, 28 probably, something like that, if everything goes well, I would say. Maybe not. But this is a very, very ambitious project. Something to add?
Any other questions?
We do all efforts.
Yeah.
Well, I can ask for the when you see the upgrade program, what is the next program for the next upgrade? So is there?
That's a good question. We are already in the next phase. Huh? We are not. We never stop. As I said, we start a rolling refurbishment of the beamline. You know the ESRF very well. There is a few beamlines that have not been refurbished during phase 1 and phase 2. That's clear.
Yeah.
And but that's not the only ones that are will answer.
Okay. So first of all, I really would like to thank you for giving me the opportunity to talk about CM02, which is a new cryo-EM CRG beamline. So most of you probably know a lot about EM. Maybe the young people didn't know that, but some years ago, it was called globology because we were only able to reach low resolution. So something like 12 angstrom resolution on measles virus nucleocapsid. And so just to have the shape of the entire macromolecular assembly that we were looking at. Some years ago, thanks to new instrument, we have been able to progress. It was still using photographic film, not the new detector, but with that, it was done. I don't know if this is working better. No, maybe not. Yeah. So we were able to reach higher resolution and able to really trace the or the backbone chain into our cryo-EM. Again, something like 5 years later, thanks to new detector, we have been able to reach pseudo-atomic resolution. And around 3 angstrom resolution, what you can see is that you can really recognize side chain of the amino acid, and you can also see the RNA, for example, and the bases. So this is not the limit today. Today, the limit is more something like that. But for that, we will need microscopes. And some years ago, again, 5 years ago, France was under-equipped. But we were quite lucky to have a high-end microscope here at ESRF, run by ESRF people, but also IBS and EMBL staff scientists. But when you compare that to other countries like Germany or UK, they are something like 20 cryoses or high-end electron microscope on these countries. We were trying to catch up and doing quite a lot of work. We were able to equip a little bit more France with electron microscopes, so new generation, 200 kV microscope, but also we were able to buy 3 new cryoses for France. One is at GBMC in Strasbourg, the other one at Soleil, and for the third one, we have decided together with ESRF and or between ESRF and IBS to install it at ESRF, just close to ID 29. So the microscope was delivered in June 23. A hutch has been built, and the microscope has been reconstructed. And I would like to take the opportunity to introduce the staff that are running the microscope. So Gregory is the technical responsible, and so Felix, Pauline, and Lefteris are the beamline scientists. So microscope, the first beam was in January 2024. But then we were running into quite a few problems. And so the inauguration only took place last November. And I also signed off for the microscope. Yeah, it was 15th of October. So what can we, or what is this microscope? It's a transmission electron microscope from Thermo Fisher. It's a generation 4. The first cryos at ESRF is generation 3. 300 kV, high energy, cold feg, high coherence of the beam, autoloader. We can load 12 different grids. Latest direct electron detector plus filter and all the software that are needed. What kind of experiment can we do? We can do single particle analysis, but also cryo-electron tomography. So when you got such an instrument, you need to do some tests. And I forgot to mention that we are also offering, thanks to CM01 and the IT team from ESRF, pre-processing service. So when you have a new instrument, you need to test it. And in EM, we don't have the lysozyme, but we have what is called the apoferritin, high symmetry particle, quite large, with 24-fold symmetry. And so here we were able to reach 1.3 angstrom resolution on this sample. But this is just a test sample. So what have we been able to do in real life since the installation of this microscope? We are able to work on high symmetry particle. It's an aminopeptidase from Bruno Franzetti's team, 500 kilodalton in size, and so also high symmetry, 12-fold symmetry in total. And we have been able to reach a resolution of 1.6 angstrom. And you can see here the active site of the of this particle. So high symmetry, high resolution, and high molecular weight. If you go a little bit down in molecular weight, this is the influenza polymerase, 250 kilodalton in size, asymmetric, so it's an heterotrimer, no symmetry, but also with this kind of sample, with this microscope, we were able to reach 2.1 angstrom resolution. And this is the work of Stephen Cusack's group at EMBL. And just to give you an idea of how the map looks like, so that's the protein that are inside the polymerase, but it's also producing some RNA with a template, and there is a product, a template, and so you can also have an idea of the quality of the map that can be processed or obtained with this kind of microscope. So if we again go down in molecular weight, that's another result that we were obtaining with the group of Martin Weich at the IBS. So it's the photoreceptor complex between a tetramer of H in complex with a DNA. So no symmetry also, and 100 kilodalton in size. So again, quite good resolution. This is the DNA, this is the protein. And when the sample is not totally homogeneous, what you can also do is do that. You can also try to see the flexibility. So just sort the different particles and get an idea of how flexible the particles are. So you can really process particle 140 kilodalton in size, which are flexible, and get several structures out of that. Finally, for single particle, that's the record at the moment. It's collaboration with David Kobesi, who was at the IBS and is now at CEA, and it's the work of Gregory. So this is a really low molecular weight particle, only 65 kilodalton in size, dimer, and out of this 65 kilodalton, only 40 kilodalton are visible. And again, this is the map that we got, or that Gregory got, 3.6 angstrom resolution. And when you fit the AlphaFold model into that, you see that it's quite good. Huh? And they were not able to crystallize that, probably because of this part that are flexible in this particle. So this is for single particle analysis. So when all the particles are quite similar, quite homogeneous. But what we can also do is tomography. And when you are doing tomography, what you are doing is to tilt the sample. And at the moment, we are only doing tomography molecular or single particle tomography. The next step will be lamella on cells once the new instrument that we just bought at the IBS will be installed. But again, working with the lysozyme, the cryo-EM lysozyme, doing tomography on the apoferritin. Again, it's Gregory's work. We were able to, by doing subtomogram averaging, get a 2.9 angstrom resolution on that one. So the system is working. Again, real life is the work of Alessio. At the EBS, we were also doing tomography on bacteriophages which are infecting or which are connected to mini cells. And by doing that, acquiring several cryo-EM data, cryo-electron tomography data, he was able to reconstruct the tomogram, and then just focusing on the part that is the part of the bacteriophage that is interacting with the mini cell, he was able to reconstruct that part by doing subtomogram averaging. At the moment, it's only 20 angstrom resolution, but with bin data. And what is really amazing is that in parallel, some years ago, with Cécile Breton, we were able to obtain the same part in vitro on single particle analysis. And you can really see that this part here is very similar to that one. And that's exactly where we want to go. So we want to do high resolution work, either by X-ray, NMR, cryo-electron microscopy, and then put that back into the cellular context by doing tomography. So these were the results. So maybe that's also interesting. How can you have access to this microscope? First of all, the grid have to be pre-screened. There should be some evidence that the sample can go to high resolution, so it's not a screening microscope. And then for the experimental time, it's a CRG beamline. So 1/3 of the beamline is available for ESRF people, so through bags or rolling access, and the rest is accessible to French or international people. We are at the moment discussing to have just a centralized access with Soleil and IGBMC. But at the moment, you can just send email to this contact. And it's also, of course, accessible through Instruct Eric, if you want. And with that, I just want to finish by acknowledging all the people for the purchasing the instrument, human resources, ESRF for all the work that has been done for everything, IBS, Strasbourg, because Bruno was coordinating this EquipeX project, CRG staff, and the CM02 staff. Thank you.
Okay, so good morning, everyone. So today we'll be speaking about the new bag, the new block allocation group bag, Chronos. And before I go in details in the goals and the real functioning methods of the bag, I will just give you the initial motivation. So this is a map of habitability of Earth, not in 2 years, not in 10 years, but this is present day. So this is scientifically speaking, the place where you can no longer live peacefully. This is not getting better in 2100. And you might think that because of climate change and the country is particularly vulnerable to climate change, this is the only one that are affected. But as you can see in Europe, in Spain especially, you had the flooding in Sevilla that were already showing that how vulnerable we are in Europe to climate change. It's also affecting us quite nicely. And all this catastrophe could be somewhat prevented because this knowledge is known for a long time and we have an idea about what's going on. But we need also to see how we can scientifically support and how ESRF can support for climate change. For this, you need to go back to the basics. This is atmosphere. Atmospheres can hold around 750 gigatons of CO2. This is technically what we can do. But what we can do also is, as humans, to produce more than 40 gigatons of CO2 per year, plus deforestation that adds 5 gigatons of CO2 per year. And this was the numbers of last year. This prediction for 2025 is even worse. We are going to an alarming number of 55 plus gigaton year of CO2, which is absolutely incredible, which means technically that in 30 years, you can technically fill the carbon reservoir at atmospheres. What used to be 20 years is now 13 years. So we need to find alternative carbon reservoir. We know that we have the biosphere with 2,300 gigatons of CO2. We have the oceans with 40,000 gigatons of CO2. But the acidification of the oceans and the deforestation are showing that this carbon cycle reservoirs are a bit limited. This is a natural process, but we are already saturating. There is another reservoir that is well known. This is rocks. It's 600,000 gigatons CO2. This is technically where we can store CO2. This is in fact the natural process. Instead of destabilizing natural system of CO2, we can simply take CO2 and put it back where it belongs, where we found it, underground. So this is now to see if we can make this from an engineering point of view happening. And this is where ESRF can help, because as you know, ESRF is a great tool for imaging. It's a great tool for observing processes ongoing into any kind of experiments. We have also the new EBS that has greatly improved the coherence of ESRF. And now the short beamlines that we had before pre-EBS are reaching the level of coherence of our famous long beamlines that were dedicated for coherence. And of course, the long coherent beamline are even better with the new EBS. Also allowed some very great projects like the project BM18, where we have an unparalleled quality of images. So we have the mission, we have an ID. Now the question is if we can observe anything with the ESRF and on this topic. So we did an experiment a bit more than a year and a half ago. We took a basalt and we just made some water with saturated CO2. It was a collaboration between ILL and ESRF. This is why it's also very nice. And we saturate the basalt with this soda stream water. And we just wait, cook it for a few hours, and see if we have a reaction happening in the basalt. This is a well-known method. This is a big project like CarbFix. And when we look at this result, we see that we have a beginning of formation of carbonate inside the basalt. So this is very promising, but the frustration is that we are only tackling the beginning of the experiment. If we want to really understand these processes, to make it fully react, we have to wait at least 1 year and a half to have the full process happening. And this is why we created Kronos. This is why we created this new bag, which is meant to conduct long-term experiments at ESRF. Before ESRF was meant to make short experiments over 3 days. Short is relative, of course, but over 3 days and not over a year. Now what we want to make with this new bag is to allow a new mode access that is allowing to have long-term experiments. As precise by Jean a bit earlier, this is led by Jessica McBeck, who was a Young Scientist Award of last year. And the allocation group is, as said, to make continuous observation of long-term processes. It includes geological processes, but not only. It also can be any scientific topic, and we have different topics, but also industry. So it requires to make recurrent scan on a week or a month base, beamlines with fixed detector and sample stage. We have to get extremely stable beamline because they have to make the exact same parameters over the year. And of course, we need to have optimized experimental designs and setup to be as quick and as efficient as possible. And accessorily, also a small place to store all this setup during the year of experiment. So we don't have only mineral trapping, even if it's probably one of the most exciting one. We have also fault healing of a fault after an earthquake, how long it takes for a fault to heal and be able to make again an earthquake. Magma instabilities, when you have two magma mixing and making very explosive eruption. We have also deep geothermal energy, olefin dissolution, battery cycling and fatigue, looking at the battery failing of a natural death, let's say, and also green concrete and cement. So far we have 11 projects as varied as fault healing and production of hydrogen. We have 2 on natural disasters, 2 on in-situ climate change, 2 on ex-situ climate change, 2 on alternative energy industry transition, and a small exotic one on paleontology, which is to look at the shrimp decaying over time. All these projects are starting at different times. The 2 on ex-situ climate change were already started this semester because the Kronos just started this semester. And 7-11 projects are also planned to start during the current weeks and next months. And finally, 2 projects with very difficult experimental setup are expected to start this summer. So we have attracted also numerous people from over the world. Each time, technically, that we give a talk, we have 1 or 2 groups that are interested in applying for Kronos. So fortunately, I don't give talks too often, otherwise my life would be hell. We have India, Oman, South Africa, and US that want to join, and we are just considering to see if we can have enough time to include them. So 2 beamlines that we are using for Kronos are BM05 and BM18. We have 15 shifts on both. BM05 is more focused on high resolutions, and BM18 on large objects. If you look at the energy compared to the voxel size, you can see that BM05 is really focused for high resolution, and BM18 for high energy and low resolution, but they have a very nice overlap, which is very practical when you want to switch from one beamline to another because of some unexpected problems. We have about 50 minutes per proposal per week, meaning that we are really using the time as efficiently as possible. For doing that efficiently, we have automatized everything ahead of the launch of Kronos. We have looked at making everything automatic. That includes also to have a strong work on developing personal setups for every project that are homemade, that are in-house developed. And we have also automatic change of the optical setups during the same night between projects, automatic change of resolution and feature tracking on a single experiment, auto-centering and automatized sample alignment. All these things normally were used to be done by humans. This can be done now automatically. We have also a whole bunch of experimental setup, as I said, that were developed in-house. So it goes from the very simple one where you have only a sample mount for the robot with sample on top, and that goes automatically, to the most complex one where you have in-situ experiments with high temperature, high pressure, and automatic pop-up of the sample to be able to scan them. We have also not only developed the acquisition, but also the reconstruction. We have developed, in collaboration with the network Excite, a new method, a new pipeline to make automatic reconstruction and automatic analysis of the systems themselves, meaning the digital volume correlations and also all the vital lag segmentation to make it as much as possible automatic and requiring as little as possible intervention from the users, meaning that the users only thinks about science. And this is it. This is my final slide. So far we are right on time with Kronos. We were planning to have the pilots in the end of 2023. We did in beginning of 2024. We launched early 2024. And now with 2025, we launch all the big proposal, all the big setup that are now ongoing. And in 2027, we will see if Kronos was a good idea or not. So thank you.
Okay, thank you very much. So I'm the last to talk. So today, data analysis is not just the only thing between you and your publication. It's the last thing between you and your lunch. So I will try to be timely. So I'll be presenting some evolution for data analysis services. Something which is provided by 2 groups at ESRF, so the algorithms and scientific data analysis group, but also the software group, and more specifically the data automation unit. So the challenge that we have today is that, I mean, we have an increasing user community. I mean, if you look back 20 years ago, I mean, we had lots of people who were really experts in synchrotron. This is less the case today, which is good. I mean, we want a large scientific community. And we also have a very large data throughput. I mean, with faster detectors, more photons, and so on. So we need to work on this, I mean, to improve the data analysis, because we want to have a greater percentage of data which is actually useful, which means also that we need to provide a timely analysis, so online data analysis during the experiment as close as possible to the data collection. And for this, we need to provide a certain number of tools for visualization, for automation, high performance computing, and so on, and really to be accessible and efficient for a large user community. Now, and there are a number of, I would say, pillars that we use for this. I mean, high performance computing and machine learning. There's also automation, and there's the accessibility of the compute tools, the interfaces. And there's the question of sort of the exploitation of open data, which is going to be very important. Now, if you look at the first part, which is high performance computing, so this is something that we've done for some time at ESRF. I mean, you can have a border diffraction, azimuthal integration. That's something which has been available for some time, but today we want to do this in the kilohertz regime. And this is integrated with a data acquisition software. So this is the second version of Lima 2, which is doing this. Similarly, we have similar approaches, for example, for serial crystallography, where we want to analyze and to veto images as they come and find if they have peaks and see if we can also compress the data. We want also to have fast iterative algorithms for coherent X-ray imaging. I mean, we've gained, almost 2 orders of magnitude in terms of data collection. So we can do a 3-dimensional coherent imaging experiment in a few seconds. We want also to be able, this is on ID16B, a live tomography reconstruction. So update a volume which is reconstructed every few seconds. And then we also want to tackle a very large data set like tomography for very large volumes. So that's an example of a violin, which has about 10 to the power 12 voxels. And we want to be able to reconstruct that without too many issues. So we are doing this already. So this works. These are just a few examples. But of course, these tools are nothing if you cannot make things easier for the users. And this is where the automation comes in. And so this is why you've been hearing a lot about eWorks, which is the ESRF extensible workflow system. So this was devised by Wout de Nolf. So we've had for a long time at ESRF a number of workflow systems for MX, for BioSAX, tools like BiPushFlow or DAU. This approach here in eWorks is more general. So it allows the systems to be deployed on many more beamlines. More than half of beamlines are using this. And here's just an example where you can do spectroscopy data processing to go from your raw data to the normalized and the Fourier transform data. And this can be used for almost anything, and spectroscopy, scattering, tomography, MX. This is really general. And this also provides a kind of unified interface and a unified API for everyone. So one of the examples of the use of its workflows is, of course, in macromolecular crystallography. So there have been some new developments. Here you have an example of a display of merged data sets when you're processing low symmetry crystals. And this is something that you can see directly on the data portal. Also, on the data portal, you have new workflows like the ones we can allow to verify the quality of time-resolved crystallography. And we've heard about cryo-electron microscopy, and there's now the integration of the Scipion software with new workflows for model building and also for tomography. All those pipelines, when they can be automated, can also be reprocessed directly from the data portal. So we're trying to unify, when it is possible, the different tools that we have available. Now, there are more developments to come, which are ongoing. So, we have just started several multi-year developments and all combining tailored processing with workflows and graphical user interfaces, for example, for dark field imaging, for powder diffraction, not just on a single pattern, but on large maps. Imagine that you've measured, I don't know, 1 million powder patterns. We want to be able to analyze those and extract some quantitative analysis, and it could also work for SACs. More spectroscopy workflows, more tomography pipelines. I mean, what we are trying to do here is really finish the last mile, something which really makes a difference on the beamline, so that we really have all the tools which are necessary. Of course, serial crystallography to provide really online processing and enable serial crystallography for a larger user community. Grain mapping, so for DCT, so this is with ID11, and also having workflows for coherent X-ray imaging as well. So these are just part of new projects which are beginning right now and which are growing. So of course, another important tool which is available to us these days is machine learning. And so we've started developing a number of toolkits. I mean, this is an example here on powder diffraction on a cultural heritage sample here, where you can take the original powder pattern, remove a background, and then find, using inference, what is the probability of having the azurate phase at different position on the sample. So in this case, you need to have some idea of the phases which are present up to, I mean, say 2,000 CIF files, and then you can see where the maps are, what is present on the map. So there are other things which we know work using machine learning, notably for imaging and tomography. That's denoising, and that's also segmentation. I mean, you've already seen all those examples, and we would like to have these tools more generalized. A smaller type of application that we are looking into, we have several PhDs on machine learning, is for example, you take a spectroscopy. This is absorption spectroscopy with XANES, and then you can have machine learning that tells you, okay, here, there's a probability of 84%, but this is an octahedral symmetry, which is a bit trivial in terms of information, but sometimes it can be very useful if you're looking at a lot of patterns. If you're just looking at one, you're going to do an analysis. But if you have 1 million, then this can start making a difference. Now, there are other things like, for example, reflectivity. I mean, doing quick analysis, automated analysis, and this is useful for operando acquisition. And there's, again, another PhD which is going to begin with this with the University of Graz. Now, the difficulty with machine learning is that we want to introduce tools, but we need to find those which can be used on a large number of experiments, which is the challenge. I mean, there are some tools which work for many things, but other tools work really for specific samples, and they are harder to generalize. And there's also the question of automated acquisitions, and we're always looking for ideas about exploiting machine learning to automate more everything on the beamline. Now, in terms of accessibility, we have several ways to access the compute tools. So one of these tools is Visa. I mean, Visa, this is a remote desktop that you can access through the web. It gives you a virtual machine with a CPU, more or less powerful, and possibly also GPU. This can be used before, during, and after the experiment. So, you know, I mean, you can prepare the tools if you want, and you can use it for, I think 2 months or 3 months after the experiment. What is important in terms of usability is that it can be shared between users. So one user creates it, and you can share it with other members of your team or someone away, and that's can be quite practical. There's also for the people who are familiar with notebooks, notably with Python, Jupyter Slurm. So you can create an interface and do your own analysis in a way which is similar. And you can even create some small interfaces if you want. And this gives you access to the compute cluster, where today we have 100 GPUs and more than 5,000 cores available. And on the cluster and on workstations, you have many software modules which are available for data analysis. And if you think that another should be added, I mean, you just ask us. I mean, as long as it's open source, it's not a problem. If it's commercial, well, we can still discuss it. And one of the last 2 things I want to mention is that, so you asked a question earlier about what should be given to the users, which is a very important question. So we've been discussing, I mean, the priorities and the important developments with the beamlines, but what we want to think about is also to establish for all the beamlines a kind of standardized list of what I would call deliverables, okay, where we have what we should give to the users, not just in terms of data, but in terms of software. I mean, and if we can establish this for every single experiments, then we will be able to do some more long-term planning. So this is something that we're going to work on this year. And I think this is very important. So, I mean, obviously we've already have had this kind of discussions, but never so formalized. So we're going to try to progress like this. And if you have some feedback, I mean, you users, and then just, I mean, send it to us. You can also tell your local contacts or use the experiment forms and reports to tell us that something should be done, something didn't work, or some new tool would be very useful. And the last thing I want to say is that, as what was already shown, I mean, open data can be very important because your data can have a second life. So this is an example of open data that you can see on the data portal. And it can only work if you also help us to make your data fair, so reusable. And for this, we need really a good metadata. This allows you to be cited for the data that you collected, or it can also help you to be collaborators of another team who want to exploit your data. So I think it's beneficial for everyone. So if you can input better metadata in the data portal and also in the experimental report, this is very important. I just want also to point out that today, the experimental report now also has a 3-year embargo. So if you want to put detailed sample information there, it's protected for 3 years. It was not the case before, but today it's more free. And we should be able to data mine this, I think, in the future. And well, this is all for me today. So thank you.